Welcome back. So in our last lesson, we talked about parametric equations and what they were and kind of how to graph them. Today, we're going to talk about them in relation to calculus. So we actually have a parametric form of the derivative. dy over dx is equal to dy over dt over dx over dt when dx over dt is not equal to 0. That seems pretty straightforward. We also have a second derivative, second derivative, d squared y. That's not how you read that, so don't do that. It's going to be the derivative with respect to t of our first derivative divided by the derivative of dx with respect to t. Okay? Can you see how that happens? So we took this, right? This goes here, take that derivative, and then put it over dx over dt. And our third derivative is going to be the derivative of our second derivative, this here, over dx over dt. All right? So let's actually put these into action and use them a little bit. We're given the parametric equations, x equals 2 cosine of t and y equals 3 sine of t. And we are asked to write the rectangular form by eliminating the parameter. Okay, so I'm going to do this kind of in that beautiful trig way so that I've got x over 2 equals cosine theta and y over 3 equals sine theta. I'll do that squaring. So beautiful. So I end up getting x squared over 4 plus y squared over 9 is equal to 1. Remember, I do like a giant addition sign here. These add up to 1, and I don't even change these. I just have them there. So what do we have here? Well, we can graph this. Looks like we're going to have an ellipse. Isn't that cute? A nice little like football, rugby ball, eyeball, whatever you want to think about there. And we want to actually find the slope of this curve at theta equals pi over 3. Well, let's first find, we're going to go up here, right? We're going to need these to use, so just keep those in mind because I can't keep them all on the screen at once. So we're going to find our slope by first finding dy over d theta. You know, usually we would use t, but in this case we're using theta. And dx over d theta. So dy over d theta is going to just be 3 cosine theta. And dx over d theta is going to be negative 2 sine theta. Cool. So dy over dx is going to be equal to 3 cosine theta over negative 2 sine theta. Great, we found our dy over dx. That really wasn't too bad, but we do actually need to evaluate this at theta equals pi over 3. So that's going to give us 3 cosine of pi over 3 over negative 2 sine of pi over 3. Kind of back to, that's about here, right? So that's going to be 3 times our cosine is just going to be 1/2 over negative 2 times radical 3 over 2. Can do some math here. So I end up getting negative radical 3 over 2. Oops, there you go. Okay, cool. And then we can actually write the equation of the tangent line through this point. Well, the point is when x, well, first we need to find the point, right? So x is going to be 2 cosine of pi over 3. Cosine of pi over 3 is 1/2 times 2 is equal to 1. And y is going to be 3 sine of pi over 3. So that's 3 radical 3 over 2. Why do I feel like I've missed something here? Nope, I haven't. Okay, so our point is 3 radical 3 over 2. Cool. Now I can write my equation. Y minus 3 radical 3 over 2 is equal to m, which we already found, negative radical 3 over 2 times x minus 1. And I'm actually just going to stop here. I don't want to simplify anymore. I don't want to waste time with that. This is it. We did it. We wrote the equation of the tangent line through the point. All right, let's go through some more examples here. Okay, So now we're asked to find all the points, if any, of the horizontal and vertical tangency to the curve. And then we could use a graphing calculator to confirm our answers, but I don't know if I'll do that or not. I might. We'll see. So first, if we're going to find a point of tangency, we need to know our derivative. And in order to find our derivative of a parametric equation, we need to find derivative of just x with respect to t and y with respect to t. So let's do that first. So dx over dt is equal to 1. And dy over dt, why do I keep writing it like that, is equal to 3t squared minus 3. Okay? So our dy over dx is equal to 3t squared minus 3 over 1, which is just obviously 3t squared minus 3. Okay, so now we need to know when we have points of tangency. Well, in order to do that, we're just going to set our derivative equal to 0. You've done this before. So we have 3t squared is equal to 3. T squared is equal to 1, so t is equal to plus or minus 1. So when t is positive or negative 1, we are going to have points of tangency. So let's actually find out when is that happening. Well, when t is equal to 1, x is going to be equal to 1 plus 4, which is 5, and y is going to be equal to 1 minus 3, which is negative 2. So we should have a point of tangency at 5, negative 2. Right? What about when t is equal to negative 1? When t is negative 1, x is going to be negative 1 plus 4, which is 3. Y will be 1 plus 3, which is 4. Oop, did I do that right? Negative 1. Oop, nope, I did not. Negative 1 cubed is still negative 1, students. Okay. Negative 1 plus 3, which is equal to 2. Good. So then I should have another point of tangency at 3, 2. All right? And these are horizontal, just so you know, but let's actually check this in the calculator. I'll show you how to do it. Okay. So on our calculator, if you go into mode and you go down here, your calculator is currently probably in function mode. And you're actually going to change this right one and go to PAR, which stands for parametric. Ooh, exciting. So then once you go to y equals, you can see that you're now going to have an x sub 1 of t, y sub 1 of t. We're changing our graphs a little bit here, right? So actually, I can graph my equation. Where did they go here? Right up here. So I'm going to graph that x is going to be t, and if you use the same button, the x, t, theta, n, now we're finally going to use that t part. So we're going to have t plus 4, and y is going to be t cubed minus 3t. And I can graph that. I wish I'd had this in standard mode. Maybe I should do that. Okay, cool. I've got something there. Maybe I should zoom out a little bit. I've got a graph here. So I don't love how I'm zooming, but hey, it's here. So I can actually trace the point 5, but sorry, I'm not going to trace 5. I'm going to trace t. I'm going to trace t when t equals 1. You can see I've got like 5, something there, right? And when I trace negative 1, oops, clear. Maybe I graphed it wrong, but anyway, that's how you graph it. I don't really care if we check this particular problem on the calculator. I think this work here is fine. What I do care is that you know how to actually graph it on the calculator, okay? Let's do another one. We want to determine the t intervals on which the curve is concave up or concave down. Well, when do we use concavity, or how do we calculate concavity or determine when it's happening? We're going to use our second derivative, so that's going to be fun. So first we need to find our derivative. So dy, let's do dx over dt, is going to be equal to cosine, right? Derivative of sine is cosine, so cosine t. And dy over dt is going to be negative sine of t. That's easy. So our dy over dx is equal to negative sine of t over cosine of t, which interestingly enough is negative tangent of t. Oops, I wrote that very weirdly. Negative tangent of t. Okay, So now we actually need to find our second derivative. Well, our second derivative, I'll write it down here, I guess. D squared y over dx squared is equal to the derivative with respect to t of our first derivative, which here is negative, I'll just use this, negative sine of t over cosine of t, divided by our derivative with respect to x. Do not forget this part. Absolutely do not forget to do this part. That's seriously the biggest mistake that students make when it comes to parametrics. So over cosine of t, all right? So I don't want to do all this math, so maybe you can do it in your free time, but basically this comes out to be -1 over cosine cubed of t, which is very fun. So now we need to figure out when this concavity is happening, right? So cosine cubed of t, cosine cubed of t is equal to 0 when t is equal to pi over 2, right? So basically our second derivative doesn't really exist, but anyway, let's do our test here. So we're going from 0 to pi, and we've got our pi over, or not just 2 pi, but just a pi. Just a pi. Just a pi. This is pi over 2. That's pi. And we can test our concavity here. So this, if I tested like 0.75, and here if I tested like maybe 2.5, and I test this, I will find that my second derivative here is negative, so it's going down, and here it's positive, so it's going up. And actually I'm going to do it since it's concavity. Concave down and concave up. I like drawing the little concave. I think it's just cute. So this is concave down from 0 is less than t is less than pi over 2, and up from pi over 2 is less than t is less than pi. Okay? Let's just talk one last thing about arc length in parametric form. So arc length in parametric form is going to be in the form arc length s is the integral from a to b of v of t dt. Well, what's v of t? The integral from a to b of dx over dt squared plus dy over dt squared, the square root of all of that. Okay? So basically, we're just using our previous information about finding parametric form derivatives and using them to calculate arc length. So we want to find the length of one arch of the cycloid with parametric equations x equals theta minus sine theta and y equals 1 minus cosine theta. Okay, well, dx over d theta is going to be negative cosine theta, right? Nope, 1 minus cosine theta. 1 minus cosine theta. Derivative of theta is 1. And dy over d theta is going to be equal to sine theta, right? So now I can actually calculate my arc length. Usually one arch is from 0 to 2 pi, and in this case it is also. So our arc length is going to be equal from 0 to 2 pi of the square root of 1 minus cosine theta squared plus sine squared theta, right? D theta. If I expand this out, I get 0 to 2 pi, the square root of 1 minus 2 cosine theta plus cosine squared theta plus sine squared theta, d theta. These become 1. So I get 1 minus 1 is 0. No, 1, is this plus? 1 plus 1. It's 2, goodness. I'm a mess today. 2 minus 2 cosine theta, d theta. And if you evaluate this from 0 to 8, do that on your calculator. Don't hurt yourself. It is 8. Okay? One final example here. The path of a baseball is modeled by the parametric equations below, where x and y are measured in feet and t is measured in seconds. Graph the path of the baseball and then find the difference between the horizontal distance the ball travels and the arc length of the path of the baseball. Okay, I'm going to graph this actually on my calculator, but before I do that, since this is in degrees, I've got 70 cosine 50 degrees t and y. I need to make sure that I'm in degrees. Okay. Go to y equals here. So I will have, 70 cosine of 50 t. I want to 70 cosine of 50 t. And I'll have 2.5 plus 70 sine of 50 t. All right, let's graph that. Ugh, so weird looking. I think I need to adjust my window here. So my t max is 0, my t 0 minimum is 0. T steps are probably fine. My x, I can probably start at 0, and let's take our x max to 20, and y actually is all be probably also fine. Ooh, maybe not. Maybe I should adjust my y. Let's get y maximum up to 20 and y minimum to 0, because oh, it's in seconds. So let's do 200. Let me adjust. Okay, sorry about that, students. It turns out I was forgetting there's a minus 16t squared here. Don't freeze, don't freeze. Okay, there's a minus 16t squared here, and I didn't have that typed in, so I was getting this straight-ish line, and it was a huge mess. But what I wanted was an arc here, right? It's a baseball, so you're throwing it. It's going to land eventually. All right. We're going to graph the path of the baseball, but good, we did that. And then find the difference between the horizontal distance the ball travels and the arc length of the path of the baseball. Okay. Well, if I graph this, I'll just, it's kind of like that, right? When x, if I trace at 0, at time t equals 0, we're at 2.5. When t is 0, we're at 2.5, 90, right? So we're 90 feet above. Is that right? Okay. Okay. Because these numbers are so awkward, I think it'll be easier to actually change them into like approximations and use our calculator. So x is approximately, I already typed this in, 44.99513 t, and y is approximately 2.5 plus 53.62311 t minus 16t squared, and when y is equal to 0, t is approximately 3.39743 seconds, okay? So when t is this many seconds, x is going to be equal to 70 times the cosine of 50 times 3.39743, which is about 152.8678 feet, right? Okay, so now we can actually calculate what, like this is our distance here, right? So now, our horizontal distance, excuse me, this is our horizontal distance. And now I can calculate that actual arc length. Well, my arc length is going to be equal from 0 to 3.39743 when it ends, right, from when it starts to when it ends, of the square root of 44.99513 squared plus, that's my derivative of x, plus 53.62311 minus 32, t squared dt. And I'm not going to put this in the calculator because it's just boring to watch, but that's approximately 184.4890 feet. So our arc length is 184-ish. Our horizontal distance is 152-ish. So if we do some subtraction, the difference between arc length and horizontal length is approximately 31.621 feet. Okay? All right, I think pretty good. Questions, leave them in the comments, and I will see you in class. Bye.